This is 2012 FRQ number 1 in the calculator section. All right. The temperature of water in a tub at time t is modeled by a strictly increasing twice differentiable function w, where Wt is measured in degrees Fahrenheit and T is measured in minutes. At T equals 0, the temperature of water is 55 degrees. So that means initially we start at 55 degrees. The water is heated for 30 minutes, beginning at time T equals 0. Values of Wt are selected at times T for the first 20 minutes are given in the table above. So this is a table. This is when the water starts being heated. And at 4 minutes, they measure the temperature. This is the temperature at 4 minutes, temperature at 9 minutes, temperature at 15, temperature at 20. Okay. Use the data and table to estimate the change at 12 minutes. Show the computations that lead to your answer. Use correct units, interpret the meaning of your answer in the context of this problem. So w prime of 12, since we don't have the function, we use these two values to estimate the change in between. So you take y2 minus y1 over x2 minus x1. So part A, you go y2, so w prime of 12 is equal to w of 15 minus w of 9 over 15 minus 9. W of 15 is 67.9 minus 61.8 over 6. That gives me 6.1 over 6, which is about 1.0167. So what does this mean? That means that water temperature is increasing at a rate of 1.017 degrees Fahrenheit per minute at T equals 12 minutes. So water temp is increasing because it's positive at the rate of 1.017 degrees Fahrenheit per minute at T equals 12 minutes. So that is how you interpret the meaning of the answer. All right. B, use the data in the table to evaluate the integral of the rate w prime of t from 0 to 20. Use correct units. Interpret the meaning of this integral in the context of this problem. So the integral of 0 to 20 w prime of t dt. All right, taking the anti derivative of w prime is w, so w of t evaluated 0 to 20, which is same as saying w of 20 minus w of 0. W of 20 is 71 degrees. W of 0 is 55 degrees, so that's 16. What does that mean? That means from time of 0 minutes to 20 minutes, the temperature has increased by a total of 16 degrees Fahrenheit. So from T equals 0 to 20 minutes, the temperature increased because it's positive by 16 degrees Fahrenheit. Okay, that's it for part B. Part C then says from 0 to 20, the average temperature of the tub is 1 over 20 times the integral. Use the left Riemann sum with the 4 subintervals indicated by the data in the table to approximate the average. Does this approximation over or underestimate the average temperature of the water over these 20 minutes? Explain your reasoning. So first things first, we want to use a left Riemann sum, so LRAM. Remember, LRAM means we don't use the last measurement. We use everything in the t-table except the last one, right? Okay, so part C says 1 over 20, that's the average, 0 to 20, w of t dt. So this is where the left Riemann sum is. So what is that? That is equal to, so here's the width, between 0 to 4, that's 4, times the left endpoint, so that's 55. And then the next width between 9 and 4, that's 5. And the left endpoint is 57.1. Plus the height between 15 and 9, that's 6. Times the left endpoint, 61.8. And last but not least, between these two, the height of 5. And then left endpoint, 67.9. All right. So this gives me a beautiful total of 1,215.8, and now divided by 20 because that's the average, we get 60.79. Right. So is this an over or underestimate? Well, this says that the function is strictly increasing. So no matter what, this function will be increasing, meaning that it can concave down and still increase. It can concave up and still increase. So if you do LRAM, you will see that left endpoint is on this side. Left endpoint is always going to be under Same thing here, left endpoint, left endpoint, left endpoint, left endpoint. So if it's increasing, my left endpoint is always going to be under. So because it's strictly increasing, my LRAM is an underestimate. And the reason is because WT is increasing. Okay, all right. Part D. For 20 to 25 minutes now, the function W models the water temperature has the first derivative given by this W prime. Based on the model, what is the temperature of the water at T equals 25? So this is only from 20 to 25. So what temperature did I start at 20? I started at 71 minutes. So to get at 25 minutes, so at T equals 25, that means I start at 71 degrees plus the integral of 20 to 25 of W prime of T, which is 0.4 root T cosine of 0.06 T dt. All right, so this is where your calculator comes in. Let's see, I'm gonna punch in math 9, turn it on, math 9, my function 0.4 root T, close my parentheses, cosine 0.06 T, close my parentheses, comma X, comma 20, comma 25. All right, so how much temperature change? It's only a 2 degrees difference. So add that to 71 that I started with. At the end of 25 minutes, I am at 73.043 degrees. So 73.043 degrees Fahrenheit at T equals 25. Okay, that's it.